This video will focus on the Vesper theory. Specifically focusing on the learning target, I can draw the shape and predict the bond angles of molecules using the Vesper theory. So as a reminder, what is the Vesper theory? Vesper stands for valence shell electron pair repulsion theory. And the idea here is that when we are dealing with covalent bonds where we're sharing electrons around the center, we've got 8 electrons usually positioned somewhere around our center element. And those 8 electrons repel from one another. So the idea is the shape that the bonds and the lone pairs will take around the center is to minimize repulsion. Therefore, they're going to be as far apart as they can get from one another. So our structure that we end up making in terms of the actual three-dimensional structure will have the lowest possible energy because the electrons will naturally be as far apart as they can. If you try to press them close together, you're going to need energy to hold them there, and that doesn't happen. So we minimize the energy by maximizing the distance. So here's just a couple things that are going to help you most with understanding Vesper and molecular geometry. Number one, when we assess geometry, we assess it around the center. So once we center an element and we bond things to it, the question is, what is bonded to the center? And how will those things that are bonded, basically, what shape will they make in space? Okay, so that's one thing to focus on. When I talk about molecular geometry, I'm talking about the geometry around the center and what space or where the location is of those bonds that are on it in the actual structure. Number two, you're going to hear me talk about something called electron domains. So when we talk about the Vesper theory and the fact that the electrons want to minimize repulsion by maximizing distance, we have two different types of electrons. Okay, we have the unbonded electrons, okay, those what we call lone pairs, those two dots that are paired together on the atom, they need a space, okay, because they will take up space. And then we also have our electrons that are in the bond. So there are two different types of electrons that need to get far apart from one another based on this theory, bonded and lone pair. Sometimes then when we talk about bonding, we talk about electron domains, which are just spaces where electrons have to hang out, spaces where electrons need room. And those electrons can be in a bond or by themselves, but either way, they need space. So I might use the term electron domain coming up this week, and it just means it's a space that holds electrons, whether they are bonded or not. So here are your 5 basic shapes. These shapes are all, again, with the elements bonded to the center. And each shape really just depends on how many bonds you have. So the linear structure at the bottom is if you have 2 things bonded to the center. That will make a line or a linear shape 180 degrees from one another. 3 things bonded, they take 120 degrees. That's how they maximize their space, minimizing repulsion. And that shape is called trigonal planar. If you have 4 things bonded, in order to minimize repulsion, the angle is 109.5 degrees, and that shape is called tetrahedral with 4 things, like Tetris. 5 things bonded is up on the upper corner, and for that one you have 2 angles. You have a 90-degree angle and you have a 120-degree angle. That one's called trigonal bipyramidal. And then if you have 6 things bonded, all the angles are 90, and it's called the octahedral. So these 5 first shapes are all, if you have no lone pairs on the center, okay, all you have are bonds, these are the shapes they take on. There are more shapes than this. There are 2 others that I'm going to have you guys be responsible for, and those 2 others have to do with what if you do have lone pairs on the center. Geometry is really only looking at what are the geometry of the bonds, but the geometry of the bonds are affected by the electron domains. Okay, so here's an example. If you have carbon dioxide, okay, if you look at this atom, you have carbon in the center and 2 oxygens on the outside. There's 2 bonds to the center, so this makes a linear structure. Okay, those 2 atoms are naturally 180 degrees from each other. But what happens if there were 2 bonds on the center and there were lone pairs? The deal with Vesper is that both the electrons that are represented by these bonds and the electrons that are lone pairs need space. So if this structure with 2 bonds also had 2 lone pairs on the center, this would not be the shape anymore. Okay? This becomes the shape because you have 2 sets of lone pairs and 2 bonds, and all 4 of those things need location. This is more like a tetrahedral then, except the 2 sets of lone pairs aren't seen because they're not bonded. But they still need space. Okay, so this is more like 109.5 degrees rather than 180 because the lone pairs that are up here need space. And to minimize repulsion, these 2 bonds have to bend down to give room. So there are 2 structures that we run into when you have dots or lone pairs on the center. So if you have 3 bonds and 1 lone pair, you end up with a trigonal pyramidal. So rather than trigonal planar, it becomes pyramidal because that region where there's 1 lone pair, 2 electrons, needs room. The one where you have 2 bonds, okay, again, 2 bonds, but instead of having 2 bonds with no lone pairs, you have lone pairs on the center, then the structure is considered bent because you still have 4 electron domains, and to minimize repulsion of those 4 electron domains, this is the structure we take on. A structure that's similar to a tetrahedral because there are 4 electron domains, but those 2 electron domains with lone pairs aren't visualized. So it's fairly easy about this topic for most people is there's no variation here. Every time you have an atom that on the center has 4 bonds, it is a tetrahedral. Okay? There's no other name, there's no other instance. So this first one on the screen here with some unknown atom in the middle and 4 bonds to it, that will always be a tetrahedral, always. The next one down where there are 3 bonds to the center, in this case, 1 is a double bond, 2 are single. It doesn't matter, it could be 3 single also. That would be called a trigonal planar because anytime you have 3 bonds to the center, it's trigonal planar. The next one down with 2 bonds and 2 sets of lone pairs, that is called bent. Because anytime you have 2 bonds and any lone pairs, whether it's 1 set or 2 sets, that's considered bent. The fourth one down with 2 double bonds, that's linear. Anytime you just have 2 bonds to the center with nothing else, that's considered linear. Then the last one with 3 bonds to the center and 2 dots, that's trigonal pyramidal. Okay, anytime you have 3 bonds, it's trigonal. With no dots, it's planar. With dots, it's pyramidal. So do the form. I would recommend possibly watching video 4.2 with hybridization. That has to do with electron domain. If you get those 2 topics kind of together, Vesper structures and hybridization, they kind of build off each other. So go ahead and do the form and have a nice night.